Yeah, unfortunately, this system removed from the core. Some people removed from the core, but they are coming back. Sorry about that. And then, yeah, sorry about that. Sorry about the confusion because I forgot to start recording of this session, which is pretty important. And yeah, so what we are going to cover is what we are going to understand is how to add capital cost and to solve long-term investment plan, but not really about the investment plan, but it's more about the capacity expansion. So the benefit, the reason that we need to use this capacity expansion is because we should be able to optimize how much capacity should be built for each technology. And it will support mid to long-term scenarios. I mean, the capacity expansion that we are going to do is going to cover only 1 year of time frame, so it's not really long term. But if you have a little bit of imagination so that you can set the demand to be the future demand, then it becomes a future scenario analysis, right? And we have cost optimal deployment, which we will identify cheapest generation mix for given demand and policy target. And we using the capacity expansion, we will be able to understand, we will be able to assess policy itself. We can test impact of emission capture, renewable targets, and tax subsidies, and etc. And we are also apply this capacity expansion to transmission integrated planning. So for example, is it cheaper, is it better to expand the power generator or expand the network or transmission itself, which is better? That's where capacity expansion can, that's what capacity expansion can decide. So there are many different examples of capacity expansion. One of the things that you can you can find this kind of applications quite often. US state level capacity expansion pathways with improved modeling of power sector dynamics within a multi-sector model. So as you can see, this did not cover only power sector, but also covered other multi-sector model based on which uses power demand and also applied several different scenarios. That's what we do. And many of my papers are also about the capacity expansion. How much wind or solar do we need, and how much nuclear do we need to reduce certain amount of emissions or to meet the certain emission target. So that's what we can do using capacity expansion. So there are a couple of things that you need to remember. First is we are going to use investment cost. Also, it's called capital cost. And if a generator, storage unit, or transmission line has a phenom extendable through, pipes can build new capacity, or pipes can decide the capacity amount, like how much capacity that we need. And the cost of building of this capacity is specified by capital cost. So the capital cost of this pipes is almost always currency per megawatt or currency per megawatt per year. You can actually decide, but usually you use just currency per megawatt, right? I mean, here when I say currency, it can be US dollar or Indonesian rupiah or South Korean won or whatever you like. So it's not defined. So that's what something that you can just decide to use it. As far as you stick to only one currency, it's all fine. Don't mix up with two or three different currencies in pipes. It doesn't work. And the cost enters to the objective function directly as part of total system cost. And in the total system cost, in the system cost, we have operational cost, which we already used quite often. What is it? Is marginal cost. So basically, investment cost plus marginal cost is the objective, is the total system cost. I mean, not entire system cost, but basically the total cost that pipes uses to minimize or to find the cost optimal scenario. So far, so good? Or am I speaking too fast? I always feel that I speak too fast. Okay. Thank you coming back, Hyunwoo. Sorry about that. Somehow this Google Meet said I needed to remove you, exactly you, because of the system error or something like that, and then you can rejoin later, something. So yeah, sorry about that, making you a bit uncomfortable, inconvenient. And we are going to use three different attributes. One is phenome extendable, not expand, extendable. And then two others, which is phenome mean, and we will use phenome max. So phenome extendable is to let PIPSA to decide the optimal installed capacity via linear optimization. So if we set phenome extendable false, which is default, then PIPSA will not decide or will not optimize the capacity. So we need to turn this phenome extendable to true. For which one? Whatever the component that you want to actually apply this capacity expansion. For example, when you have 5 different generators, if you want to apply capacity expansion algorithm to only one generator, you can just turn phenome extendable of the generator to true. Then only one generator will be used in the capacity expansion, right? When you apply this capacity expansion, you can decide phenome min and phenome max. So phenome min is a minimum capacity. You can set it to be 0, or you can set it to be 100 megawatt. Okay, phenome max is the other side, the other way. So you can set the maximum amount or capacity. So this will avoid to have a over expansion. For example, having 1,000 terawatt of wind power in South Korea, which is not realistic at all. So we can set the maximum amount of each generator, not the entire carrier. So we are going to do this task based on our week 3. Okay, I guess everyone has this Jupyter notebook with you. So let's go through just line by line to recap what we had done so far during the week 2 and week 3. Okay, first we imported the PIPSA and Pandas library, and then later we imported Plotly, which is a library to plot the result in a bit more beautiful or cute way. And then we create network using PIPSA network. Be careful, you always need to have capital N when you say network, when you define new network. If you just type like something like this with a lowercase, it will not work. Okay, always capital. And then we set the snapshot to be from the first day of 2024 until the last day of 2024 or 2024. And then we added 2 carriers. One is gas, another is bio. And by the way, I'm checking the message always. So if you have any problem or question, please let me know. And we are going to import data. For those of you who don't have this data file, please go to the drive, Google Drive, and then you can find it on the data directory. But if you are in the last session, I'm pretty sure you already have this data file with you. And then we set 3 nodes. So we have bus 1, we have another bus 2, and we have a bus 3. And then not last. And finally, we set the load. Maximum capacity is 100 megawatt. And then the demand pattern that I provided is capacity factor. So the maximum is 1 and minimum is just a 0, right? So we multiply this capacity factor with the maximum capacity to create a load pattern, okay? And then we limit the length of the modeling period to be only 12 days. I think it's 12 days, right? 10 days, 20 days, 20 days. 20 days of the first of 20 days from the first hour of 2024. And then we generated, we added generators, one gas one generator, which is connected to bus 3, and each capacity is 50 megawatt, and each maximum P max PU is 1.0. What is P max PU? P max PU is the amount that this generator can provide. So basically the maximum capacity factor. If P max PU is 0.5, then gas one will be able to provide the electricity up to 50% of each P norm, its capacity. And then we have marginal cost, which is 50 currency per megawatt hour, but let's say just dollar. And we set it as a gas. And we have gas 2. Basically same with gas 1. However, each PNOM is 30 megawatt. So each capacity is 30 megawatt. And its marginal cost is slightly cheaper than the first one. And then we have a bio connected to bus 2. And then its capacity is 40 megawatt. And its Pmax PU is 1. And its marginal cost is 30. So $30 per megawatt hour. Each carrier is bio. And we have all those generators and demand component. To run the model, we need to connect those generators load to using the link, all those buses. We need to connect all those buses into the system. That's what link or lines would do. But we use the link because link is be more, how do I say, straightforward. We set link 1 and 2, or 1 to 2, which is first bus is bus 2 and second bus is bus 1. It's a bit annoying when it count from 0, right? And each capacity is 100 megawatt, so you can this link can have up to 100 megawatt of electricity through the link. If it goes more than 100 megawatt, it can't accept it. Efficiency is 0.9, which means to send 100 megawatt to this link, generator need to provide about 111 megawatt of electricity, roughly, or maybe just 110, right? And then we have another bus connecting bus 3 and bus 1 with the same attribute. And we run the model just to test it. We ran the model to test it, and then we set a commutable true. What does this commutable true mean? Commutable true makes this system to be, or this generator to be unique commitment, which means pipes can turn on or off this generator. So if you want to have only one generator to be available to be on or not, then you can set only one generator, or gas 1 or gas 2, whatever you like, commutable true. And we have a startup cost, and we have P min PU, which is when this generator is online, it must provide over a certain threshold of electricity. So in this case, it's 20% of each capacity. So the reason is technically, if this generator provide, let's say just 1% of each capacity, then the electricity output is not going to be stable in many cases, but it's very pretty much generator by generator and turbine by turbine. So this value is not very general number or something. So you need to find the correct number. When you actually make your own model, you need to find your correct number from the generator, from the utilities or power electric generation companies, or sometimes market operator. In case of South Korea, this PMIN PU is decided by the market operator. In Jeju Island, its PMIN PU was about 60%. Now it became about 35% or something like this. So it was unnecessarily too high. And we have ramp up limit, which is the speed that hourly speed that this generator can increase its capacity output. For example, this is 20%, right? Every an hour, generator can increase its output 20% of its capacity. So usually it's around 10%. More than 10% can be a little bit tough for generators due to efficiency issue. And also generator needs some time to heat up as well. So that's why we have minimum uptime and minimum downtime, right? Minimum uptime means in this case, minimum uptime is 5, which means when the generator is on, it must be online for at least 5 hours, right? If there is a room only for 3 hours to be online, then this generator will not provide electricity to the system. And mean downtime is 2. So if it's off, then it must stay off at least 2 hours. That's what we said before. After we ran this unit commitment, we changed committable to false. Why? Because we wanted to calculate the marginal cost, right? So we set the status fixed, which means we got this status from unit commitment, and then we used this fixed status we define the status of each generator based on the unit commitment to run economic dispatch, because those two are pretty much not available to run altogether, because one is MIP based and the other one is LP based. So we are going to run LP after that, and then we get the result, right? That's what we went through during last 2 days. It was pretty big, right? It was pretty busy. So we are going to run it, and then we'll see the result. Now this is the result we should have. Is it all good? Everyone has the same result. If you have an error, pretty much the error is due to the data, missing data. This data/demand 2024.csv. There are two questions. Should we add some code for bus 3? Because I believe code let me double check it. We don't have bus 3 here. We must have one. Yeah, we have bus 3 here. Probably we didn't have bus 3 in week 3, and it might be my mistake, but now we have bus 3 here, which is connected to generate 1. And actually, during there are some people who did the homework from the last week, and I found very interesting output, which I'm going to share later, not right away. After we do this, the first week 4 session, I will share very interesting findings. And then we are going to turn network generators committable to true, because when we ran the last optimization process, we were doing the economic dispatch, which we turned committable to false. However, to have this capacity expansion, we need this to be a committable true. We're going to run it. And then let's try optimize it just in case if this works fine, right? Always it's good to just run to test when the model is small enough, because sometimes it takes such a long time to get the result. All the same here, right? And then what we need to do is we are going to add some numbers to run this capacity expansion. Network generators T norm is 0. It means that we are going to turn all the generators' capacity to 0. network generators P norm extendable is true. So now we are letting pipes to decide the capacity of all the generators. If you want to fix the capacity of, let's say, two generators, get two gas generators, and if you want to just let pipes to decide the capacity of only bio generator, bio power plant, you can do that as well. It doesn't need to be zero for entire generators, but because we are just testing, we are learning this process, we are going to just do the entire generators to be zero. Network generators commutable force. Now we are going to turn this one to force again. I mean, yeah, I actually wanted to do something else. Let's not turn this to force. Network, optimize it. Let's try to optimize it to see what happens. Yeah, when there are lots of generators, we definitely have some problem putting all the values like this. So I'm going to tell you how to do it, how to make things a bit faster to apply to the real world situation later. Okay. So the output is infeasible. There was a slightly explanation that I had. Actually, the reason that I put the commutable to true is because I wanted to tell you that this capacity expansion doesn't work with unit commitment together. Sorry about that. It was my mistake previously. Capacity expansion must have commutable force always. Then if we run it again, oh, sorry, what? Did I make any stupid mistake here? Sorry about that. Let me just run it. We have optimal. Okay,
Sanghyun?
Charles. Yep.
Yeah, I can see your commutable has a typo.
Thank you. Thank you so much. Now, see, thank you, Charles. You saved my life.
Nah,
So yeah,
just echoing my classmates.
thank you so much. Okay, so yeah, always this when you do this capacity expansion, commutable must be false because capacity expansion works with linear programming, not the mixed integer programming. That's unfortunate, but that's how these pipes work. Pipes works actually. So the commutable must be false to run the capacity expansion. So we have this output. So what is the actual output? We can you see the capacity, but not yet. We wanted to put some more numbers to make things be more interesting. We have generators, and we are going to change the value of gas 1, and we are going to set its capital cost to be 800,000. Copy and paste, but this time for the gas 2, let's make it slightly cheaper. The next one is what we have, bio, which is 1. As you can see, this underscore is like a comma. But when you have underscore in PyPsa, you have no problem in using this as numeric value. However, if you actually have comma, it will have a problem. So underscore is the best way. Of course, you don't need to have it like something like this. It's not must, but for me, having underscore is much easier to see how many zeros that I have. but sometimes you have million of them. Now we have capital cost. So what we can guess is if there's no big issue, probably guess 2 is going to be the cheapest, is going to be the one which will have a largest capacity, followed by guess 1 and bio, because that's what capital cost is. But let's run it and let's see how it looks like. Another typo. Okay, it worked. There's no error. So that we are going to print, let's say, network generators dot p nom opt, which means opt underscore. Sorry about that. This is the capacity, optimized capacity after the capacity expansion. Let's just see what it look like. So basically, we have full of gas 2 and small amount of bio, and we have negative gas 1. But forget about that negative value, because optimization algorithm doesn't always find perfect optimal output. Sometimes it can be small negative, or sometimes it can be slightly positive. But if it is 0.00000012 or something like that, you can just assume it as 0, because anyway, it doesn't affect the result much. Okay, now we want to see the investment cost. Network generators P nom opt. Now it's the capacity multiplied with network generators capital cost. So this is how much is paid for each generator. Right? So basically 0 for gas 1 and a lot for gas 2, and about, I don't know, about 1/7 of gas 2 in case of bio, which is a bit cheaper. So that's the result we have. And then I'm going to share one of the function that we had before. I guess we had that somewhere, we had that plot function in the last semester, in the last session, right? Let me double check where the function is. Must be, I must have it somewhere from the last session. Okay, this is the one. I'm going to copy and paste it to here. Plot. Okay, copy and paste this code to one of your cell. Then we will see the output. Okay, this is the generation output. Basically, it's all about gas 2. Oh, there is question from Hyunwoo. Can you show some code for capital cost after network generators that ROC gas 1 capital cost? I can't follow the question. Can you elaborate a little, if you don't mind? Or is this one? I think maybe this is the one. So we setting the capital cost here, 800,000 and 700,000, and in case of bio is 1.2 million. Each fine number can be slightly different, then the result is going to be different. However, it doesn't affect the entire lesson and entire training process anyway. So this is the result. It's just all about gas and slight amount, small amount of bio. If we zoom in, as you can see, it's just all gas too and small amount of bio, which is not really, how do I say, reasonable in or realistic. But we need to set some more. The reason that we have such number is because we didn't have a proper min and max boundary. So we are going to set network generators dot ROC guess one, and we are going to set P nom min equals, let's say in this case is 10, which means guess one can be up to 10 megawatt, right? Then copy the entire line to the next. This next time, for this time, we are going to set the maximum to be 80 megawatt. Then copy those two lines. We will make the value for gas 2. Let's make this gas 2 be smaller because the previous one was boring. Sorry, it was problem of my English. And then the next one, we are going to set the boundary of bio as well. Bio, for bio, in case of bio, it can be 0 up to 50. I will stop here for maybe 10 seconds to make sure that everyone can follow. Okay, let's go to the next line. And then we will run the model. Because we can assume the result, the gas 2 was the cheapest one, right? But now we limited its maximum capacity to be 60, so that the model will have more gas 1 or bio, this bio output. The reason the gas 2 was 100 megawatt is because the maximum amount that bio can provide was 100 megawatt to the system. But now it's only 60. So if we run it, we have optimal output, so that we are going to see the output using the function plot network. Okay, if we run it now, we have a bit different result, right? So as you can see here, if we zoom in a little more, then we have gas 1 and gas 2 and small amount of bio. The reason that we have bio, though it is the most expensive one, is because there is a transmission limit, which is 100 megawatt, so that this gas 2 and gas 1 can't anyway provide more than 100 megawatt to the system. So that's the reason why this happened. First thing first, what you need to do is go to our drive, Google Drive. Go to the Google Drive, and then if you go to data, you can find two files, Ninja PV and Ninja Wind. Please copy and paste it to here. This. There are other files which we will use later during week 6. These two files are basically the reason that its name is Ninja is because it's from Renewable Ninja. That's a website. You can type renewable.ninja, and they provide quite a good renewable energy generation related information, sometimes potential of the certain area, and then also you can get renewable energy generation pattern as well. So we are going to use the generation pattern of renewable ninja. So everyone copied and everyone already got this data in your folder, in your directory. Okay, at least I have one person alive, two alive. So nobody was really responding to me. I thought I was talking to zombies. Actually, I love the song Zombie of Cranberry. I think it's Cranberry, right? I love that song. So, yeah, let's jump in. Let's go to the last part, last cell, so that we can add some more. So what we are going to do, we are going to add network carrier. And then its name is obviously renewables. Finally, we have renewables. And network add, it's a generator, right? It's still a generator, PV generator. Its carrier is renewables. Be careful about the typo. First, we are going to connect it to bus 1. And then its capacity is 20 megawatt. Capital cost equals 500. And we are going to add wind as well. Carrier is renewables, obviously. Bus 2. Let's connect it to bus, to the second bus 2. And then capacity is 50 megawatt, 15 megawatt, 1.5. Capital cost is 700. Okay, this is the system. And if we see the network, now we have 5 generators. If we see the generators, we have 5 generators, 2 gases, and 1 bio, and 1 PV, and 1 wind, right? And we are going to import data set. This time, let's say it's just PV profile equals PD, read underscore CSV. Obviously, this method will read CSV file, right? And then ninja underscore pv.csv, but index is 0. Also, because the index is a date, this is how it should be. Probably the Windows is too zoomed in too much. Is it okay to see? Or maybe this can be better. This could be better, right? And then we are going to have wind profile. Copy and paste. But this time it's not PV, but wind. Then if you run it, yeah, this is another mistake. This shouldn't be index. Sorry about that. Index column. So we need to specify the index column. The number of the index column is 0. So the first column is the index. So if we see the file, that data that we imported, this is it. We have a snapshot, and then we have PV output, which is capacity factor. Maximum is gonna be 1. That's what I set in the data set. Then we will have PV profile, which has no index from PV profile, reset index, and will drop true. Same for wind. So easiest way is gonna be like this. Wind, change to wind. Now if we see the head, no index. So now we don't have index column, right? We only have the value. The reason that I set this way is because the data set we have has a snapshot from 2019, but our snapshot is 2024, so it is going to have a crash, so error. So we just remove the snapshot to be able to use only the value. There are two different ways of setting this wind and solar pattern as renewable, but let's try the first one, network generators interesting dot p max. Okay, what kind of error is it? Probably there are some other people having error, not sure. It says name error. Exactly the same. Up to 33, and you had an error here, right? Probably your directory structure is slightly different. So 33 is fine. What about 34? Okay, then this one had an error. I cannot see any reason to have an error here, unless you had a typo in PV profile, something. I will copy and paste this code to the message. Then will you do it again if it solves the problem? Hope it works. Huh. So wind profile is not defined means you don't have this one. The second one. Should try wind profile dot head. Probably you might have a typo somewhere here, right? Yes, I was correct. I was not a bad trainer. Okay, let's see this one. Now we are going to put the profile into the generator information. So for the first one, we are going to have PV and PV profile, no index. Is this correct? Before you run it, there is a wrong part. We actually need to have underscore T after generators. The difference between network generators and network generators T underscore T is a temporal information. So in case of network generators, it only has a technical information such as capacity or cost, marginal cost, or mean up or mean downtime, and etc. and etc. However, if you have underscore T, it accepts time-based information, right? And we will have the same for wind as well. Wind profile, no index. What's going to happen if we run it? And let's see, optimize it, because we changed the value in the middle. I'm not sure if we can optimize it, but hopefully optimal, right? So this is what we have. Just in case, I'm going to copy and paste this to our message. If you have a trouble, you can copy and paste mine. And if we see the result, it is going to be interesting. Five-star plot network. Seems like there is some problem with mine as well. Let's double check it. Pmax, PU, wind, and we have a capacity, pinum mode. Interesting. Because I was supposed to have a wind here, but I don't have one. Seems like PV and wind are too expensive. Why is it? Because we had extendable true. So we are going to change it. We are going to have them fixed. No, this is correct. The pinum true. Yes, it must be correct one. Sorry about that. Give me just 1 second to understand what happened. Let me change a couple of things here before we run it. Okay. Let me go down here. Network generators dot pnom extendable equals force network generators dot pnom equals in this case, let's say just 50 is just too big, I think. Let's try with 50 and then optimize it. We have optimal solution. Then we will. Sorry, I was stupid this time. What I wanted to do was pipesa plot network. Then we have a little different result. Let me just go in and see what happened. We have gas too, and we have bio, but we don't have wind. What happened? So let's debug together. What happened to my code? Did I miss the bus? What happened? Bus 1, we have bus 1. We have bus 2, Hinom. And we have bus and carriers, propel generators. Links are connected. Couldn't see any reason to have such an issue. But just in case, let me go back to the beginning and then we run it to avoid any issue with it. Let me remove the marginal cost, bring it back to the original one. And then we have capital cost. So far, so good. Don't need it. Renewable, let's go through very carefully. We have renewable and we have capital cost. We have we have capital cost. Is the capital cost right? And then marginal cost equals 0 just in case. And both are connected to bus 2. Then let's see the network, particularly the generator. We have generator, but this time network generators P nom extendable equals force, and then we get the profile, wind and solar profile. This is correct, right? P max PU, P generators, P max PU. Before we run it, let me just double check it. Network generators on the T has some value, but what I want to see is P max PU. See, yeah, I found the problem. I failed to put the correct values into the generator's T, time temporal information, because I missed some part. The PV profile we had has a much longer information. PV profile that underbar no index is a much bigger one. It's pretty big one with 8,760 hours, but we have only 480 hours in our snapshot, right? That was the problem. Sorry about that. And then values, and welcome to my life. This kind of debugging is just my life always. Values. Now we have putting the value here. Yeah, don't laugh. And then let's see network generators on the T dot P max PU. Now we have the value. Yay. Okay. We are going to optimize it. Thank you, Yanu. We are going to optimize it again. Thank you, Faris. And then if we, yeah, the problem is now it became infeasible. Why is it infeasible? Interesting, right? The reason that it became infeasible is because we have too much capacity as well. So that actually causes trouble. So the thing that I have to change is this part. Make it true. And then actually I have to set up wind, but where is it? Yep. Override true. Sorry about making all the complicate this debugging, but I will go through line by line again after I manage to make it with you guys. Okay. Then this should be fine. It's optimal, right? If we see it, ta-da, can be different, hopefully. Yay! See the difference? We have gas 1 and gas 2, but what we have at the same time is PV jumped in and small amount of wind as well, right? Because I made all the mess here, I'm going to go through just once again to make sure that everyone understands what kind of mistake I made, okay? It's all good. It's all good so far until here. We needed to set up. We actually didn't need to set up the marginal cost, but we had to set up this generator PV and generator wind, right? Everyone is following so far here, right? And the reason that I used overwrite equals true is because I already have PV and wind generator. I needed to overwrite the information. If we don't have it, it can't. It just failed to overwrite it, and it will not give you error. It will give you the warning that it's not overwritten, right? And then we are checking the network if things are all correct. And some of the generator can be extendable, some may not, but it depends. But in this model, we turn everything into extendable, so that even wind and solar can extend each capacity as much as they like. However, you can remove that part as well. And then we imported wind profile and solar profile and checked each first 5 lines to see if numbers are correct. And then put them into the generator's Tmax PU. But before, I told you that there are 2 different ways of setting this. Usually, you may want to use Pmax PU, but the other way you can do is you can actually you can have a set, which means in case of Pmax PU, it explains maximum capacity factor that can be used. So this profile or this capacity profile of PV and wind became the maximum level, right? So when it is 0.251, if this network doesn't allow, or if this pipes doesn't allow, it can generate only 20%, so 0.2, and ignore the other 5.1, right? However, if you use PSET, it doesn't matter how much cost you need, 0.251 must generate when must be included in the network, right? So PIPESA doesn't decide how much of PV or wind will be in the system in terms of generation, hourly generation, but it will just use the fixed capacity factor, right? That's the difference between PSET and Pmax PU. And then we optimize it, and then we have the result. So it was a bit tough day. I made a couple of mistakes, couple of bugs, and a couple of small mistakes. I wanted to say it was intended, but it wasn't. So can't lie about that, but it was very interesting. So that's what happened during the renewable integration. So let's go back what we did. So the reason that the difference between normal generator and wind or solar generator is because it has time varying availability, right? When there is sunshine, when there is wind, it will generate electricity. However, when there is no wind or no like solar, no sunshine, it can't generate electricity, for example, at night, right? So compared to normal generators, which can provide electricity almost always, as far as there is enough gas or uranium or like coal, solar and wind need its own capacity factor pattern, hourly pattern, and then market will decide how much of capacity will be used. So the objective was to understand how to integrate renewable into pipes, and I understand it was a bit fast and it was a bit tough for some people, but it's okay. All you need to understand is you need to use generators under T rather than just a generator. So network generators under T and P max Q or P set, depends on what you need to use. And then we can use it. But forget about this. These are the things that we are going to do next week. So this patch model is basically based on hourly system. Here we used Renewable Ninja to get the PV and wind profile. However, there are some other options. For example, you can use ERA5 database as well. I'm going to explain you what's the difference during week 5, but ERA5 is was quite popular, but it has its own problem, and Renewable Ninja is been more popular these days. However, it also has its own problem. So depending on what kind of data set you need, what kind of analysis you want, you need to choose it carefully. And we also based on this renewable energy integration, we can test like how much of battery and hydropower or hydrogen like gas power will be needed, which are all coming next to 2 weeks later. After we have renewable, there are two other things that we are going to understand or analyze. We are going to able to understand and analyze. One is how much energy storage is required. Of course, it is really important. That will include batteries and pumped hydro storage. And also, we will try to understand how this renewable and solar renewable generation capacity will affect transmission constraint, because renewable sometimes generate a lot, sometimes not. So that actually is a big burden to the network operator. However, it is not always bad burden. There are solutions that you can use. So we are going to test it. So this is the result that we saw before. So that's what we did. So we included solar and wind. So basically the chart is almost exactly same with our output. With this one, right? We have a gas, and then PV and wind, and small amount of bio, of almost zero to cover it. That's what we had. So yeah, that's what we covered today. And then we updated the model. So again, be careful when we update the model, we need to use generators T. I put them twice because this is really, really, really important. The difference between generator and generator T is, in case of generators, it is, in case of generators, it is technological specification, such as capacity, and generators T is time varying information like capacity factor and how much it can be generated, right? So this could be the result a bit different, but this could be the result that we had. If gas 2 was extendable, it might generate a little less, or if gas was cheaper and more expensive than PV can provide more. Or if we use is set, where is it? If we use, come on, yep, rather than P min, P max, PU, if we use, say, set, the result could be quite different. However, because we have P min, PU, and P set both at the same time here, it caused a problem. So couldn't see the result, but I will update this code for you to be able to have a look at the difference between P set and P min, PU. Okay, that's what we did. And today we have a small homework, which is what happens. See what happens if we double the capacity or triple the capacity of wind or solar. Then let's share your result and let's see what is going to happen. Probably you can have a look at the marginal price as well, which could be quite interesting. As today is the last day of the first half, we are going to have break next week, and then we will come back. During the last semester, I lost about half of our trainee, our student, but this time I want to keep 100% during the next second half. Please come back. And before we go away, there are a couple of things you want to remember. First, we learned, we discussed about economic dispatch, right? What is economic dispatch? It's all about the price, right? It's all about the cost, which is the cheapest, and cheaper one comes first, will be used first, right? And then we have unit commitment. Unit commitment analysis let pipes are to decide turn on or off the power of the generator. So why is it important? Because when the unit commitment is on, minimum up and down times will be used. Startup and shutdown cost will be used. If unit commitment, so committable is false, then minimum up and down times will be ignored, right? Even if you have it, pipes are will not include it in the model. And we used linear optimal power flow. Basically, whenever you type network.optimize, it uses linear optimal power flow always. And then we also consider the security constraint linear optimal power flow. However, we will cover this bit more in details later. We integrate the renewable energy profiles into the system, which I made intentional errors to make sure that everyone is following. However, it was not really intentional. And there are a couple of components that we cover. The first is the most important network. Whenever you start, you should start with defining the network that you are working on. And then buses is fundamental node of the network. In the network, you can have as many buses as you want, but if you have too many, your computer will not like you at all. And if you have, like, say, 200 buses, then highly likely your computer will say it's not possible to proceed in this machine because memory issue or CPU issue and etc. You are actually correct, Hyunwoo. Yeah, it will create a dot curve, but dot curve these days is not necessarily bad. That's something I can discuss later. And there are a couple of important things that we used. Committable is true and false. Committable true and false for unit commitment, and then pmin pu and pmax pu. And we also covered the startup cost, shutdown cost, and also we had min uptime and min downtime as well. And yeah, that's it actually for the first half. And thank you so much for following these 4 lectures of this semester. And we will come back in 2 weeks. I will send a reminder email to everyone for the homework and for the next session. Thank you so much.
Thank you. Thank you very much, Yoon.
Thank you, Paulo. See
Thank
you
you.
on 24th.
Yeah. See you. See you.
Please come back.